So in the last class, we learnt about how to make state tables and then realize a circuit using flip-flops and other gates. Okay. Today we are going to learn how to reduce the state table using state table reduction and implication chart techniques. Okay. So for example, in the last class we wanted to design an sequential detector, a sequence detector in which if a sequence of input is 1 0 0 1, the output should go to 1, and accordingly we made this, and this from the last class. So we made an 4 states. So this was known as an state chart. So first we made the state chart, and then from the state chart we made an state table. This was the present state, and the input is the new sequence which is coming, and accordingly what was the next state and what would be the output, and from here we made an for D flip-flop, this would be the table, and accordingly we designed the D flip-flop equations, and then we implemented the circuit. This is what we did in the last class, right? And now here, once we have made an table out here, in the last class we didn't try to optimize here, like we made, like if you remember in the combinational circuit also, once we make an K-map, so we used K-map to simplify the min terms, right? Here also you can see, you can say this is all the conditions, all the conditions which is there in the state table, state chart is represented in the state table. Like so, if you are implementing this directly, it means all the min terms you are converting into gates. But in the combinational logic, what did we do? We didn't. We used an K-map technique or QM technique to further simplify that and get an optimum number of gates, right? So we use that K-map technique as well as QM technique. Similarly, here also for the sequential circuits we have two techniques, right? So we are going to learn about those two techniques, right? So the first one is state table reduction technique, right? So we start with we assume this is the state chart which is there. Okay, so initially it is in A. So if you see here, A, B, C, D, E, F, G, 1 2 3 4 5 6 7 different states are there. So for this at least you will require 3 flip-flops, and once you make a state table, so this is the state table, right? So now if you see here, here it says the present state is A, and there is one input. If it is 0, it continues to remain 0. From here you can see here, right? If it is 1, then it is moving towards B, right? So it is moving towards B here, right? So this is what, from a state table, if a given state and a chart is given, we have to make a state table first, right? So this is the chart. This chart depends on the problem statement. For different, say this could be a sequence detector, or it could be anything. For any combination, the user defined requirement. So once we have an user requirement defined, we first try to make a state chart, okay, which gives the various states for various inputs. Once this is done, we got to map this into an state table, right? So how do we map? Last time we did this, so let's try to do this also once again. So it will serve as an reminder, revision for you, right? If this is an state A, if it is 0, it is going to remain A. So state A, next state is A if x is equal to 0, and if x is equal to 1, it is moving towards B. So x is equal to 1, I have put B. And now also if you see here, x is equal to 0, this is output is 0, x is equal to 1, output is 0. So for both these also the outputs are 0 here. From B, again if it is 0, it is moving towards C. The output continues to be 0. If it is 1, it is moving towards D. right? So this is an hypothetical state chart. Okay, this could be anything like that. So if it is 1, it is moving towards D, and in both the cases the outputs are 0. So I write in a B, x is equal to 0, the state is C, and then x is equal to 1, the state is D, and the outputs in both the cases is 0. And from D, if I see here, if it is 0, it's coming to E. If it is 1, it is going to F, and the output is 1 here. So so if you see here, so there are so to reach this F, I guess from this you can see that once it is reached F, the output is going to 1, and there are several paths to reach F, unlike in the previous case. Okay, where we stated there was only one path where you could reach the output. So this is a case where there are multiple paths for the output to go one, so several sequences are possible here. So from D, if it is 1, it is going to F, and if it is 0, it is going to E, and in case of F, the output is 1, and in case of E, the output is 0. So from D, E and F, and 0 and 1, that has been written here. From E, again, if you get an 1 here, you are coming to F here, and if it is 0, you are going back to the initial state. So from E, 0 initial state, and 1, you are coming to F, x is equal to 1. So accordingly, outputs is 0 and 1 here. So that is about F, and then from F, if you see here, if it is at 0, you are coming to G, and if it is 1, you are remaining here. So G and F, 0 and 1, and for G, if it is 1, you are coming back to F, and if it is 0, you are going to A, you are to gain, right? So so this is a representation of an state chart as a state table. So this is the first thing we need to do. Now instead of straight away trying to implement this as flip-flops by, right, so we can try and optimize this. Okay, so how to do that? There are two techniques. So the first technique is known as state table reduction. Okay, so Ritika, you just joined. So we have just discussed, this is the state chart, and this is the state table. So this is an hypothetical state chart we have taken here. So this is some standard, it could be anything defined by an user. So this is the corresponding state table. So if you find, if you see here, it is from A to B, it's going A to B when the input is 1, and if it remains at A, if the input is 0, and in both the cases the output is 0. So you have written this next state, x is equal to 0 A, x is equal to 1 B, and output in both these cases are 0. Similarly for B, if the input is 1, it's moving towards D. If input is 0, it's moving towards C. So that is what C and D, these are, and then you have 0 and 0 as the output. Is it okay? Are you in sync now? Okay. So now if you see here in the state table, now this is the state table which we have made. Now in the state table, if you see, first we are going to compare the outputs, right, and also the next states. Okay, if they are the same, then we can club these two states. Now if you see here, in all these things, okay, here A, B, C, D outputs are same, but these are different. For E, if you see, it is A, F and 0, 1. Similarly for G, it is A, F and 0, 1. That means once you reach the state E, if x is 0, you are going to move to A. If x is equal to 1, you are going to move to F. And if x is 0, the output continues to remain 0. Whereas if x is equal to 1, since we are reaching F, it is going 1 here. The same is the case for G also. So for G, it is like if x is equal to 0, it is going to A, right? For here it is going to A, and for E also it is going to A, and if you see, it is 0, 0 here, and it is 0, 0 here, and from 1, 1 it is coming to F, and 1, 1 it is coming here to F. So G and E, okay, they are the same states actually, right? So we can club these two states together. So if I do away with G, then there is only one issue, right? So I can do away with G, but there is a G available here. So I need to change, since I am going to club these two into a single state, G and E. Now this G will be replaced as E. Is this much understood to everybody? Yeah, Kishan, Ritika, Sachin, is it understood? Right? You have an state table out here. You have to see if these things are exactly the same. So if they are exactly the same, then we can club these two states into a single state. So we can remove this particular row in totality, and then since we have removed G, you can remove E also, but if you remove E, then wherever E, you need to write G there. Right? In this particular example, I have just removed G here. So here G, I am going to replace it with E. Is it okay with all of you? Yeah. So so now if you see, this is the reducing. So if you see here, this G has been now removed from here. So now you have 1, 2, 3, 4, 5, 6. Initially you had 1, 2, 3, 4, 5, 6, 7 different states. Okay, so this is how we have reduced one particular state. Now again, we can have a look at this. Is there further possibility of reducing? Okay, now you have EF01, EF01. Right? So what is EF01, EF01? They are the same. So D and F. So I can remove this, right? So they are the same. So I can remove F, and since I am removing F, right, here I will find that E is going to F, but I am removing F and I am retaining D. So I need to keep this F as D and also this F as D. Okay, so I can straight away remove this particular. So now the reduced expression is none, 2, 3, 4, 5. And now again we do an inspection. Is there anything which is same? This is A, B, C, D, A, D, E, D, A, D. There is nothing more you can do about it, right? So now if you see, there is only 1, 2, 3, 4, 5. Okay, in this particular case, since there are 5 states, and still I will have to use 3 flip-flops, because I have to finally generate 3 different states. But whereas if it is an last time we saw, right, we used 2 flip-flops and we gave those different states, different numbers, 0, 0, 0, 1, and now since there are 5 different flip-flops, we 5 different states, we will have to use 3 different flip-flops, if you remember from the last class. Okay, so you will have to have use 3 flip-flops, but here initially also, since it is 7, you had to use 3 flip-flops, but the total number of gates required to realize this circuit is much lesser, because we have optimized this design. In certain cases, if it gets reduced by 1 more, the total number of flip-flops also will come down. Okay, in this particular example, the total number of flip-flop has not come down, right? So this is the reduced table. Now if once you have reduced, so for each of these states we need to assign some binary, right, some flip-flop states. This we learnt in the last state. So one option is to give a sequential number 0, 0, 0, 1, 1, 0, 1, 1 and 1, 0, 0. You can also give an gray code also, right, 0, 0, 1. You can give these kind of codes, or this is known as an one shot, like 0, 0, 0, 1 and 1 here, 1 here. But if you are using one shot, in the right, in this case you will require more number of flip-flops. In these two kind of codings, you will just require 3 flip-flops, right? So so this is how you can assign these and then further proceed with what we did in the last class. Okay, just as a reminder, we can go back here. What we did in the last class, this was a sequence detector. You had S0, S1, S2, S3. So we made this depending on this sequence. We wanted to detect this sequence. So S0, if we have a 1 coming here, we come here. If we have a 0, you come here. Another 1 here. So 1, 0, 0, 1 here, and one more 1 coming here. So this goes to high, right? So so you have 1, 0, 0, 1 being detected here with this state chart. And after making the state chart, what did we do? We made the present state and the next state and input in out here, and then because there are 1, 2, 3, 4 different states, So we gave it as 0 0 0 1 1 0 and 1 1. Even then I told you not necessarily you need to give it in sequence, you can give it in any sequence, it doesn't matter. Okay, so that is not going to make much difference, so you can give it in any sequence. So we gave that, and then so it was 0 0, and then what was the next state? Accordingly we mapped this into an state table, and having done that, then we decided, okay, for implementing it with D flip-flops, if it is 0 then D will be 0, if it is 1 it will be 1. So we made DA DB, and we wrote the expressions for DA DB in terms of QA, QB and X. This we did in the last class, right? And once having done that, then we implemented that circuit using gates. This is what we done in the last class. So same thing. So first we make, whenever there is a problem statement in sequential design, we are going to make an state chart, and from state chart we are going to make state table. And last time in the last class we didn't optimize it, and here we are going to optimize this first before getting on with the flip-flop design. We try to optimize it, and after optimizing it, what we get the state chart, this we have to implement it in the hardware. Okay, so this is the technique which we need to follow for sequential circuit designs. Okay, so again, like these are, like if you are using 3 flip-flops, the total 8 states are available, out of which only 5 we need to use. So we can use any of these, and among the 5 you can use anything. You can either use from 0 to 4, or you can use gray code, whatever it is. So that flexibility is available with us, right? Now we can take one more example out here. So if you see, this is the present state, this is the next state, and this is the output. If present state is A, if X is equal to 0, I go to F. If X is equal to 1, I go to B, and the output in both the conditions will be 0. So similarly, from the state table, I have already made from the state chart I have made a table. So let's see how to optimize this table. So this is another example which I have put in to make things clear to you. Now if you see here in this, now if you see what are the things which are common, can you see F, right? And F, B, no, they are different out here. What are the things which are common out here? Can you see something which is common? FB 10, GH and GA 10, right? D and H are common, right? If you see here, D and H are common. G and A, G, no, here the this G and A are not common, right? I can find D and H common, right? So I can remove H out here. So H has been removed here. So wherever the H is removed here, so here H has been replaced by D. So this becomes D out here, and there is another. So this becomes D out here. So this becomes a D out here. Now this is D. So one reduction we have done. Now again, if I look at this, is there anything common? These are 3 zeros, 3 zeros out here. FB, FB. Okay, A and C, right? So we can do, I guess, A and C we can combine out here. So now if I combine A and C, I am going to remove C. So I am going to put here as an A here. So that I have put A here, and I have removed C out here. Now is there any more scope? So there is nothing here. Now I think we have reached the optimized state, right? They are all different FB, FB, but these are FB, FB are common, but here you see it is 1 1 and 0 0, so you can't do that. So this is the optimized table, right? Now we can implement an hardware here. So this is like what we did for in K maps, and a similar thing we are doing it in the state reduction table also, right? Okay, and now the second technique is known as implication chart. Okay, so this is another example which we have taken. There are 1, 2, 3, 4, 5 states, and if a is equal to 0, it is going to S3, and then a is equal to 1. This is the input. A means the input, like we said x as input in the last example. Here a is the input. So if a is equal to 1, it goes to S2, and for both this a, the output is going to be 1 out here. So this is the given state table. Okay, from this table we have to find whether we can have a simplified table. So these are the various conditions which are already given to us. Okay, now how to now optimize and see whether there is a possibility of further optimizing using the second technique, which is known as a state table. So what we do is we write S0, S1, S2, S3 on the x-axis, and the y-axis S4, S3, S2 and S1, right? So if you see here, S4, the last one is missing out here, and here the first one is missing. Okay, so that we have, why do we write this? So that S0 we compare with S1, S2, S3, S4. Okay, we are going to compare each whether there is a possibility of merging. So that is the reason I have written S0 here, and I have written S1 to S4 here, right? So similarly, S3, I have stopped at S3 here, because now if you see S4 is already here. So S4 is being compared with S0, S1, S2, S3 already. So there's no point writing S4 there. So first we write all the states here. Now I'm going to compare S0 and S1. Can they be merged from the table? If I see S0 and S1, you see this is S3, S0, S2, S1. If the outputs are not matching, I straight away put an cross out here. That means it cannot be clubbed, these two states. Okay, so what about an S0 and S2? Now I'm going to compare S0 and S2 whether they can be merged. So it is S3, S3 and S0, and I am comparing S0 and S2, right? S3, S3, S2, S0, 1, 1 and 1, 1, right? So can they be merged? Yes, they can be, right? Because it is S2 and S0 I am going to merge. So this S2 and S0 is going to be the same finally. So I am right. So that is the reason, and I can merge this. So that is why I have put a tick here. Now, is this understood why I have put a tick out here? Yeah, Sachin, Kishan, is it understood why I have put a tick here? See, the outputs are matching 1, 1, and these states are also matching S3, S3, and I am comparing S0 and S2. So obviously I am going to combine it as a single thing. So that is the reason I have put an tick here. Is it understood? Yeah. Okay, so now I have put a tick here. Now what about S0 and S3? I am going to compare S0 with S3. So S0 and S3, S3, S1, S2, S3. So I have just put a cross here, so they are not. S0 and S4. S0 and S4. Okay, first and foremost we look at the output. If the output is not matching, we just straight away put a cross. So I put a cross here, right? Now with S1, S1 and S2, S1 and S2, the outputs are not matching. I put a cross here. Now S1 and S3. Okay, now is the important thing which we listen carefully what we are going to do. S1 and S3. S1 and S3. If you see here 0, 0 and 0, 0, the outputs are matching, right? So I straight away don't put a cross here. Okay, now I say this is conditional. Conditional means if S0 and S1 are same, if S0 and S1 are same, and also S4 and S3 are same, then I can put a tick here. So I write those two conditions out here, right? Is this clear? So let me repeat it once again. Now I am going to compare S1 and S3. The first thing which I have to compare is the output same. S1 is 0, 0, S3 outputs is 0, 0. So they are matching. So I straight away don't put a cross here. But then there is other issues also, because S0 and S1, if you see here, they are not, they are different out here, S4 and S3. So I put in conditional statement that S0 and S1, if they are same, and also S3 and S4, if they are also same, then I can put a tick out here. So I leave it like this. Okay, writing S0, S1, S3, S4. First I'll complete this table. Okay, I have just time being I have put a conditional statement out here, and I have left it as it is. Okay, then I move to the next S1 and S4. S1 and S4 also 0, 0, 0, 0. The outputs are matching, and what is not matching? S0, S2 and S4 and S1. So S0 and S2 have to be matched. S0, I am not writing S1 and S4 here, right? Conditional, because that is what I am going to match as such. So that is assumed. Okay, once you're doing this matching, I don't have to write separately S1, S4. So but S0, S2 is a different issue. So that I am writing that condition out here, right? So now I do that. Now I go to S2 now. Now S2 I need to compare it with S3 and S4. So the outputs itself is different. So I put both cross, and finally I take S3 and I am going to compare with S4, right? So if you see here, the outputs are same. So that means I am not going to put a cross straight away, but there is a condition that S1 and S2 here S1 and S2 have to be the same. So I put that condition here, and S3 and S1 also have to be same. So I put the second condition. So how to make an implication chart? Is it understood till this point, all of you? Yeah, if you keep putting the messages in the chat, and it will give me a feedback. Okay, now having done that, so now if you see here, this is a tick available here, right? So S0 and S2 is as such we are going to make it one. So S0 and S2 as such we are going to it is possible, right? From here we can see that S0 and S2 we already have a tick here. So that means we can put a tick here also, right? Whereas for this, if you see S0 and S1, they have to be the same. Only then I can put a tick here. Like what about S0 and S1? We have already seen that they cannot be paired because the outputs are different altogether. So S0 and S1 cannot be paired. So S0 and S1 cannot be paired. So I don't even have to bother for S3, S4 because this particular condition itself is not possible. So that's why I put a cross here straight away, right? Whereas in this state S0, S2, for the next one S0, S2, S0, S2 we have seen S0 and S2, it is possible here. Already we have decided to merge it, right? Because everything was matching here. So now I am going to put a tick here. Right, okay, so I am going to put a tick here, so the tick is missing. Okay, and what about, so these are correct. Now here wherever I have put conditional things, I'll check for that. Here I had put a condition S1, S2, right? So what about S1, S2? S1 and S2 was a cross out here already. We had seen that S1 and S2 cannot be merged, so I put a cross out here, right? Now if you see here, there is one tick out here, right? This also has become a tick now. This was conditional initially, but since S0 and S2 are the same, so there is one more tick available here. Is it understood now? So now we are going to merge S0 and S2, and also since there is a tick available here, S1 and S4, so I can merge two mergings I can do. Now if you see here S0 and S2, there is a tick out here, there is a tick out here also, S1 and S4. So if I merge these two cells, see S0, what was it? Okay, it's given here also. So S0 and S2. So S2 is been removed. So wherever there was an S2, I write an S0. So I get an reduced state out here. Similarly, I am going to merge here. Here this becomes a tick now, S1 and S4. So S4 also has been removed here. So you get a reduced state here. So wherever there was S4, I replace it with S1 out here. Now there are only three states here. There was 1, 2, 3, 4, 5 states. So for 5 states, at least you required 3 flip-flops. Here there are only 3 states. So you just require 2 flip-flops. So you see here, this is we are able to save flip-flops also, and now this chart has become so simple out here. So this becomes much easy to implement in the hardware. Okay, is it okay? Okay, so let me give you one more example so that things become even more clear. So this is another state table. It is given here A, B, C, D. So we need to try to reduce this, okay, using the implication chart. So first I have to write A, B, C, D, E, F, G. Till G it is there. So A, B, C, D, E, F. I don't write G here, and here I start from B. B, C, D, E, F, G. Right. So now from the table, if you see here, right, A and B, I am comparing A and B out here. Now if you see here, the outputs are same. That means there is a possibility that they can be merged. So, and what is the possibility? This is A. D and E needs to be same. So I write D and E in bracket. Okay, so this is a conditional possibility. There is a possibility which exists, which we will explore later on. Okay, now between A and C, you see the output is different, so we just put a cross there. Okay, and between A and D and A and E also, between A, it is 0 1 and 1 0, so I put a cross in both these places here. Now what about F? Yeah, A and F, you see 0 0 0 0, so there is a possibility that these two can be merged. And what are the conditions which will come? D has to be equivalent to C, has to be merged with C, and A requires to be merged with B. So C and D and A and B, so these are the two conditions which if we meet these conditions, then A and F can be merged. Okay, so that's how. Now what about A and G? If you see 1 0 0 0, so the outputs don't match, so straight away I put an X out here. Right, now I go to the next B. With B and A has already been compared here, so that is the reason I start now comparing with C. Right, you don't have to keep repeating that. So that is why this table is made like this, from A to F and B to C, and then the number of rows keeps reducing, right, so that we don't duplicate things. Now between B and C, okay, these outputs don't match, I put correct. Between B, D and E also 0, so these don't match. So B is 0 0. Now 0 0 is only with an F, right? So so straight away only for an F I write. And what is the condition for F? A and E have to be matched, and B and A have to be matched. So A, B and C, E. So I write these conditions here. If I go to C, it is 0 1. I don't find any 0 1s in the output, so I put an all cross out here, right? And what about D? D, if you see here, it is 1 0, so these three are not there. And then I start with an E, it is 1 0, and A D D, so it is not conditional, right? It is all the everything is same out here between D and E, so I put an tick out here, right? So this is that means it is possible. Okay, we are going to merge this because it is exactly the same out here, right? And between D and F also, if you see, it is not, so I put an cross out here. And what about D and G? Now if you see D and G, it is 1 0 1 0, but A is also matching. D and E needs to be matched, so D and E, I put an D and E, I put an condition out here, right? And then again I go to E. Now E needs to be just checked with F and G, so 0 0 1 0, so I put an cross out here. 1 0 1 0 is matching with respect to G, but it is A D and E, so I put a D and E here. And then with finally I have F and G. F and G, the outputs don't match, I put a cross here, right? So I have gotten all this now. Now these are the conditional blocks which I need to check whether. Now first is A B, whether D and E, okay, whether D and E is it possible to merge. Now if you see here, between D and E, we already have seen that it is possible to merge. Okay, so I have put a tick here. Now this conditional now becomes an tick here, because D and E is possible. We have seen that, right? D E, it is possible. D and E are exactly the same, so I have put a tick here. So this, wherever there is D E, I'll put a tick here. Now D and G can be merged, right? And E and G can be merged. D and E as such is being merged, and now A and B also can be merged. So you see, so many possibilities have come. What about this CD? So we'll have to see C and D. There is a cross here, so this cannot be merged. So this is going to remain as it is. What about here AB or CE? Right, you have to check only one. If there is a cross in one, then both have to be satisfied, right, for to merge these two cells. Now C and E, it is a cross here, so this also cannot be done here. So you can now finally, what are the cells which we can merge is DE, right, that is one, and then AB, that is second, right, and DG, third, and also EG. These are the four cells which we can merge out here. So now this is the reduced one. So all those like A, B has been merged, so B has been removed. So wherever there was an B, it has been replaced with A. Then we also merged what was it, DE. So E has been removed here. Okay. Here again E and F, so E has been removed already, so F remains, and then F and G, so G has been removed, F has been retained. Okay, so not necessarily you retain F and remove G, you can retain G and remove F also, right? So you can do that. So you will find a reduced state. Now it is only 1, 2, 3, 4. So you can implement it with just two flip-flops. Okay. So one more example which